So my title is Locality and Smoothness of Quantum Field Theories. It sounds very grand, but I can assure you it's not. My goal in this talk is to describe what I think are three, or actually four, very basic principles of physics, and to describe via examples what happens, how they interplay with each other, and what happens if we do or don't respect them. And all the examples will come from the study of generalized symmetries of quantum field theories, and I've taken them from my work because that's what I know, with Oscar Randall Williams. This pointer doesn't work. Is there a? Oh, now I can't advance the slides. So that's okay. I work with Oscar Randall Williams and Joe Smith. So before I start, I need to issue a little parental advisory. This talk is going to involve use of the C word, which is the rudest word there is for physics. It's, of course, category. And it's even worse than that, because when I use the word category in this talk, I will always mean infinity category. And the same is true for words like sheaf and topos. And if you don't know what an infinity category is, you shouldn't worry, because basically you can follow almost all of this talk if you know what a topological space is and things like what a homotopy group are. Okay, so let's start with the talk proper. I'd like to start with a little lesson from history, or rather from geography. And the idea will be, pointer doesn't work. The idea will be that I'd like to make an analogy between our understanding of quantum field theory, or quantum field theories today, and geography in 1459. So those of you who are lucky enough to get an invite to the Bezos wedding a couple of weeks ago might have seen this in Venice. This is the Mappa Mundi, which was produced by Brother Mauro in that year. And what you see is the following. Locally, we had a very good understanding of places, of geography in those days. So if you start in Venice, which is here, we understood things very well. But as you go further and further, travel was hard in those days. Marco Polo made it all the way to China. By the way, this map is upside down. It's a bit like the mostly plus convention for the Minkowski metric. Our knowledge got worse and worse. And as you can see, or at least as people in this half of the conference can see, there was one big thing that was missing in 1459. And it took a global, quite literally, global insight, namely there was evidence indirectly that these places organized themselves into something with a topology of a two-sphere, that gave someone the idea that you could start here and sail this way and get here. Now, of course, it was more complicated than that. There was something in the way. And that something in the way was itself a big discovery. And arguably, it was that discovery that led to the technology that led geography today to be able to produce images like this. So thinking globally was a big deal. And so my first principle is that we should try to do the same thing in physics, or rather in quantum field theory. We've gone a long way by starting from Venice, free field theory, let's say, and moving outwards by thinking about doing perturbation theory. But travel, perturbation theory, gets harder and harder. And when it comes to the global picture, we have some insights, you know, cyborgs like Marco Polo. We know about some dualities, we know about holography and so on, but basically our global picture, everything is a mystery. So a big step forward would be the cobordism hypothesis. Because the cobordism hypothesis says that at least the topological quantum field theories really do form a space. You don't have to think of them as a category. And there's even a geometric version which applies, or would apply, to non-topological quantum field theories. And here I should say that whenever I say space in this talk, what I actually mean is the simplest kind of space there is, a homotopy type. And when I say smooth space, what I mean is a sheaf of spaces on some smooth site of manifolds. Basically a thing that allows you to move around smoothly in homotopy types. Now, why is this a big deal? Firstly, these things really are like spaces, and let me be precise about that. Both of these kind of objects can be assembled into a topos. And a topos is a place where many of the tools of homotopy theory, of classical homotopy theory, are still true. And so you can use tools from topology to make progress in trying to understand the global picture. And by the way, once we talk about smooth spaces, then you can also use tools from geometry. Okay, All right, so one thing I should say, in the hypotheses of the cobordism hypotheses, two words appeared. One was locality and one was smoothness. So I want to say something about those as principles of physics. And locality is somehow the one which is most humorous to me because it seems to be entirely uncontroversial among participants in this conference that physics is local. I've heard the word bandied about thousands of times. To me, the fact that physics is local is the greatest miracle of all. Because firstly, I have absolutely no idea why physics is local. If you do, please tell me. But secondly, physics would have gotten nowhere as a subject if it weren't for the fact that it were local. Consider, if you will, an apple, as Newton once did. And you could ignore the text here. This is just so they don't sue me. Newton doesn't sue me. Trinity College might sue me. When Newton considered the apple, the only reason he could figure out why it goes plonk is because he didn't have to worry in those days about what actually makes up the apple. And nor did he have to worry about all the other things that might or might not be in the universe and what they might or might not be made up of to understand why it goes plonk. He just needed to think about the apple and the Earth. And so locality, I don't know why physics is local, but it sure as hell is. And I think we should always try to take it into account when we're doing our physics. Now, what about smoothness? This is also a funny one because when I mentioned this to people at the conference, it seems to be much more controversial. And yet, if you go and talk to a physics undergraduate, it's not controversial at all, because every physics undergraduate knows that physics is as smooth as you like. Every single function in physics can be made as smooth as you like. And I invite you, if you think that this is controversial, go back and register for a freshman course on physics and see how far you get with, for example, the harmonic oscillator if you don't think that physics is smooth. But the bit that I want to pick up on is really this part that in undergraduate physics, physics is as smooth as you like. Are you going to ask a question?
I'm going to say a word.
Is he allowed to do that?
It's continuous until you get to quasi-crystals.
As I said, it's controversial. The thing that I want to focus on is this smooth as you like, because there are lots of places in undergraduate physics where it's convenient for functions not to be smooth. And here's a good example. When you study waves on strings with fixed endpoints, it is very convenient for the function not to be smooth, let alone not even differentiable at the endpoints. But I worry that this principle of classical physics, as Theo calls it, as smooth as you like, becomes dangerous when you combine it with the other principle of trying to think of the whole space of quantum field theories, because this involves an ambiguity. And so there's a danger that when you try to talk about the space of quantum field theories, when you try to classify them, two theories that you might think are different because of the amount of smoothness they have, they could turn out to be the same thing. So you could be double counting or over counting. And probably sounds vague now. Maybe when we get to the examples, that will sound less vague. All right, so let's get on with the examples. They all come from generalized symmetries, and so I need to tell you what a generalized symmetry is, at least what I think a generalized symmetry is. And so you can understand that if you know about the concept of a group in mathematics and the fact that a group can act on a set and it can have fixed points, points that don't get moved by the elements of that group. All of those notions that I've just said can be carried over to any topos. So I'm going to define an external symmetry of a quantum field theory to be, you take this object in the topos that represents the whole space of quantum field theories, and you let some group object in a topos, it's an external thing, that's why I call it an external symmetry, you let it act on that object, and you say a symmetry of a particular field theory, which is a point in that object, you say it's a symmetry, or it's got a symmetry, if it's a fixed point of this action. And this is the one place where you need to know what the infinity in infinity category means, because in the infinity world, to be a fixed point of a group action in a homotopy theoretic sense is not just a property, it's not a point is fixed or it isn't, it's a structure. And how can you see that? Well, it's homotopy theory. So to be fixed is not that you fix a point, but that you move it to a point which is path connected to the one you started from. And a choice of paths is data, so it's structure. And that will be important in what follows. To say it another way, you can build an object in the topos of homotopy fixed points, which is why the H is there, and the map from that into the original object is seldom a monomorphism. Okay, so, and if you want to ask what's the internal symmetry of the quantum field theory, well, that corresponds, a quantum field theory corresponds to a point in the object, and we'll say that the internal symmetry is just the object of loops which are based at that point in X. Okay. I said before that you can do many of the tricks that you can do in homotopy theory in any topos. And here's one trick. In any topos, there is an equivalence of categories between the group objects in a topos and the pointed connected objects in that topos. And that equivalence is given by looping in one direction and de-looping in the other direction. That means that you can take all the notions that I just gave you, group, action, fixed points, and you can recast them in the following way. The group G becomes a pointed connected space, BG. A group action on the quantum space of quantum object of quantum field theories X becomes a fibration over BG, together with an identification of the fiber over the base point with the object of quantum field theories. And a homotopy fixed point is a section. So that's a map going the other way, such that when you compose the two, you get the identity. All right, so here are 4 examples that show how these principles play out in examples. So let's look first of all at why the space matters. If you look at the first paper that led to the modern craze on generalized symmetries, you will find an example in there. The example is to take a 2D oriented topological field theory, and it's the one you get by taking some gauge group, Z mod P times itself, and quantizing it. And as you know, or Digraph and Witten know, there's a choice of possible action, and so we label those by P and Q. And in this paper, they did clever manipulations of the classical action to show that this theory has both naught and one form symmetries, and that they're both isomorphic to this product of cyclic groups up here. Q is an element in Z over P, which is basically the choice of possible actions. So you take an element in that, pull it back along the classifying map, and that's a thing in C star, which you can call an action. Okay. This, however, cannot be true, because if I hand you the space of topological field theories, which are two-dimensional oriented, you can do a computation of pi1, which is the naught form group of symmetries, and pi2 of the component which corresponds to that theory, and you get answers which are completely different. In one case, you get a permutation group, and the other case, you get an infinite group. What's going on here is that these groups here are tiny subgroups of these things here. And the symmetries of any one theory are much, much larger than you might think they are by doing manipulations at the level of the classical action. And the reason is duality. Basically, there are a million different choices of gauge groups here. They all have to land on a very small number of possible theories. Roughly speaking, there's like 1 for every n, where n is the dimension of the Hilbert space. It's a bit more complicated than that in the oriented case. Okay, so this is why thinking about the space is a powerful idea. Okay, what about locality? So I want to talk about 't Hooft anomalies. A 't Hooft anomaly, at least in the days when I learned physics, a 't Hooft anomaly was a global symmetry of a quantum field theory that can't be gauged. And there's a funny thing about a 't Hooft anomaly, because it's a thing that you do on a like theory by theory basis. You write down your theory, you write down a symmetry, and then you worry about whether you can gauge it or not. And if the cobordism hypothesis is true, that is bunkum. Because the cobordism hypothesis, here's one statement of the cobordism hypothesis. It's an equivalence of categories between, you take a bordism category and you equip it with some G structure. And read one way, this says that the way to understand what this space is to compute homotopy fixed points of G action on something like the core of the fully generalizable objects, blah, blah, blah. Read this equivalence of categories, if you will, the other way. It says that the continuous symmetries, the global symmetries, sorry, which are homotopy fixed points acting on the space of quantum field theories, can always be turned into background gauge symmetries by following this equivalence of categories. So the cobordism hypothesis says that Tooft anomalies, they are an all or nothing thing. If your G action factors through the famous ON action on the bordism category, every single such global symmetry can be gauged. And if it doesn't, a projective symmetry is a really good example of something which is famously not gaugeable, then it doesn't. And there's no like one by one. So how can this be possibly reconciled with the old picture of Tooft anomalies? Well, it's because if these two statements are reconcilable, then in the old way of doing quantum field theory, some hypothesis in the cobordism hypothesis is not being respected. And the one that's not being respected is locality. Here's an example. If you take non-local, as in not fully extendable, oriented 2D topological field theories, then it's well known that they're classified by commutative Frobenius algebras. And here's an example of a commutative Frobenius algebra, which has an automorphism, i.e. a global symmetry, which you simply cannot gauge, and it's demonstrable that you cannot gauge it. What's going on? This Frobenius algebra is not semi-simple. That means it cannot be made into a fully extended topological field theory. And so it's not surprising that you can't gauge certain symmetries. You can even cook up examples where the Frobenius algebra is semi-simple, so you can extend this topological field theory, but the way in which you define the symmetry down at the non-fully extended level simply cannot lift. So you can get into all sorts of trouble, or you can just insist on locality from the beginning. Okay, smoothness. So my last two examples about smoothness, which is the more controversial thing apparently. So here's why smoothness matters. Let's go down a dimension. Let's look at one-dimensional oriented topological field theories. And let's find all of their symmetries. This is a question in homotopy theory, so you can do it. And here's the answer. All possible symmetries are you pick a group G, and then the actions, or at least the ones that emit fixed points, are classified by homomorphism from G into the automorphism group of GLN. And then the corresponding fixed points, the symmetries, are like representations of G, but they're twisted by these automorphisms in a suitable way. And that's cool on one level because it gives you many of the things which you actually see in physics. If you pick the identity automorphism, you get a representation. If you pick an inner automorphism, you get a projective representation. If you pick complex conjugation on the ground field, which induces an automorphism on GLN, you get, what do you get? You get anti-linear or anti-unitary symmetries. So you get loads of good things, but you also get bad things because no one can make this map smooth because these things are just groups. And it's even worse than that. There are automorphisms of the ground field C, which are wild. They are infinite order, and we have never seen anything like that in physics. And so the problem is, what's the problem? Well, I tell you the problem is, you need to treat these things, even topological field theories, if you want to talk about their symmetries, things like C appear, and you need to take seriously the fact that that wants to be a smooth object. Okay, so how do you fix the problem? What you do is you think of topological field theories as special cases of non-topological field theories. And you take some examples of classifications which already exist in the literature. Here's two ways to think of a topological field theory as a quantum field theory. You equip it either with a zero metric, or you equip it with a smooth map to the manifold, which is a point. There's only one of those. And when you do that, and you go through this classification business again, out pops the correct answer. The group actions now are smooth homomorphisms, if you take G to be a Lie group. And the representations themselves are like twisted versions of smooth maps, twisted versions of reputations, and in particular, these wild automorphisms have gone. Okay, so now for my last example. This one is a lot more subtle, and it's somehow, therefore, much more interesting. So here's a first observation about the topos of smooth spaces. This is a big, wild beast. And finding the external symmetries of smooth spaces is hard. I give you a proof of that fact. One example of a smooth space is a manifold. And to find all the smooth symmetries of it is to find all possible ways that a Lie group, for example, can act smoothly on it. And that's a hard thing to get a handle on. But here's something which is easy. And here's a shocking fact. In the topos of smooth spaces, if you compute pi0 of a manifold, the answer is the manifold considered as a set. So what it does is it completely obliterates the smooth structure and just remembers all the points. And here's the thing. Anybody in this room can find all smooth actions of a Lie group on a single connected component, because that's a point, and there's one action, and it has a fixed point. And so this tells you that even when you move to more general smooth spaces, like the smooth space of quantum field theories, even if you can't find the symmetries of the whole smooth space, you can look for symmetries of just the connected components, but then you have to ask the question of whether they lift. And the answer is they don't. And we called that a smoothness anomaly. And so let me tell you what the physics of this is. I basically already said it. If you take the connected component at some particular point which represents your quantum field theory, you can think of that as like a rough copy of the quantum field theory. You got the quantum field theory, but you've forgotten how it fits into the smooth space of all quantum field theories. All right, okay, so I'm going to talk really, really fast. So I just give you an example. If you take discrete quantum mechanical theories with a finite dimensional Hilbert space, the smooth space is this smooth stack. It's hard to find all symmetries of that, but if you look at a single point, then the symmetries are exactly the answer that you might guess. They're like smooth representations like before, but they have to commute with the Hamiltonian. But we're not finished because of this smoothness anomaly. Some of those things do not lift, and here's one that doesn't lift. Take the simplest quantum mechanical system that I know. It's an electron in a magnetic field. Two-state Hilbert space, the eigenvalues are 1 and -1. You can find a symmetry which is a Z2, and it's a naughty symmetry. It acts unitarily on half of the Hilbert space, and it acts anti-unitarily on the other half, and thanks be to God, it doesn't lift. But to show that it doesn't lift takes a lot of work. Okay, so I'm out of time, so I won't mention the fourth principle of physics, which I think is the most important one, so I made it the 0th principle. Here is an experimental plot of the actual space of quantum field theories. I'm a physicist, so I need to show you an experimental plot. We have so far, in the entire history of science, we have discovered one quantum field theory. It is QCD, the theory of the strong interactions. Every single other quantum field theory is demonstrably breaks down at some finite energy scale. And therefore, we shouldn't be doing quantum field theory in this room. We should be doing what every physicist is doing these days, which is effective field theory. And so I put it to you that there is a paper to be written, and Owen and I have started talking about it, but so far we haven't got any further than the title, which is this one. Thank you.